All right, what we're going to do is we're going to look at this problem here, and we have a table of time and velocity data. So I'm going to bring that over. Let me switch here. And let's bring this table of data over. So our data that we're looking at here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points of interest. So we have 10 intervals that have been created in our process here. So we have time in seconds. And let me glimpse at how that is coming across here, making sure. Okay. So we start at 0.0 seconds, then we go to 0.001. Where's our next two decimal place? And this is doing by a thousandths, so it's moving the seconds up by a thousandths. So that's our time in our table, is moving the seconds by the thousandths. Yep. And so we go from 0 seconds to 1/100th of a second. And our velocity in miles per hour. So velocity in miles per hour. It does start at 0. And then it goes to 41 miles per hour, 66 miles per hour. Let me my table. And notice, yeah, I'm recopying information. I can just read it off of the table, but I think in copying this, I'm kind of interpreting the information. Like 84, 98, 109. Some really big changes to speed here. I didn't read what this object was. What is this? A sports car. Accelerating from 0 to 146 miles per hour. Oh, it's not in seconds, it's in hours. That's my bad. See, I wrote it as seconds, but it's actually in hours. Alright, now these don't seem so bad. 36 seconds. 109, let's see, 119, 127. They did the conversion for us. So this is in hours, fractions of an hour. My bad. So all in all, this is 36 seconds. Let's see, 127, 134, 141, 146. I think I have those last couple wrong. Nope, 134, 141. So 134 here. Alright, so this is our data, and this creates a velocity versus time curve. It generally looks like this. Now, each framing here between every two brackets can be a rectangle. We have our divisions here. We have our 0. We have our first 1,000th of an hour, our second 1,000th of an hour, our third, our fourth, and so on. And so this is at 0.010 hours, and this is 0.0 hours. And we move up by a thousandth of an hour. And so at this point we have a velocity of 0, and here this velocity is 41 miles per hour. And I'm just going to draw a couple of the rectangles to get an idea of what we're getting here from this particular data. So each one of these is a data point. Each one of these creates a height. We have, and each one of these can be a left or right-sided approximation. And so if we come back to the question here, the first thing it asks us is, use the rectangles to estimate how far the car traveled during the 36 seconds it took to reach 146 miles per hour. What should the length of each sub-interval be? And what happens is the sub-intervals themselves are the delta t's. And so if we look at our delta t's, where did I go? All right, so for question A, what's the length of the sub-interval? Well, our delta t, these were all recorded with a delta t of 0.001. So that's the first part of the question. And then approximately how far did the car travel? And roughly how many seconds did it take? Let's see, approximately how far did the car travel? And so when we take our little rectangles here, if I use right-sided rectangles, then I'm going to get the sum of I equals 1 to 10, because there's 10 of them here. There's 11 frames, but we'll make 11 rectangles. And so my displacement, or how far I am from my starting position, not the distance I travel, but how far I am from the starting position, will be my velocity at a given time sub I times delta t. And so if I sum these through, my first velocity is 41, and I'm going to do I guess I'll do the trick I always do. I'll pull the delta t outside of the summation. So I'm going to have 0.001 times the sum of 41 plus 66 plus 84 plus 98 plus 109, blah, blah, blah. I'm going to add up this column. So give me a second, I'll add up that column. As you hear me getting my calculator over here, unfortunately I don't have it attached to the screen. Plus 41, 66, 84, 98, whoops, if I can actually type correctly, 98, 109, 119, 127, 134, 141, 146. And then I'll multiply that by 0.01. So having a hard time getting the previous answer on my calculator. There we go. And we get 1.0654 miles. Alright, so we do this sum and do this multiplication, and the distance we are from the starting point is 1.065 miles. And so we are taking the area integral. I'm using right-sided rectangles versus left-sided rectangles. Since this is a monotonically increasing, the right side has a little more value. I think some of the questions otherwise in the book will sometimes notice one began and ended at 0, and so it didn't matter if you did right-sided or left-sided because of the way the motion was going. Let's see, roughly how many seconds did it take the car to get to the halfway point? And so the halfway point for here would be the half area. And so if we look at 1.065 miles, then we want to figure out how long it took to get half the area in here. Let me move. Sorry, I'm moving screen here. Bump. And at the halfway point in area, well, what we can do is I'm going to build a little kind of computation here. And I'm going to look at first where the average value is. There we go. Hopefully we can see this. I'm going to scroll down a little bit here, give myself some more working space. And so the average value, b minus a, or the width of the whole thing, times the answer that comes out of the sum here, 1.065. And so b minus a is this value here, since we started at 0. So 1.065 times 0.1. Get my calculator back out. And so on average it was going, divided by, not times. If I did a multiplication, it should be divided by. The average velocity was about 106 miles per hour. Sorry, this is a division here. It's 1 over this. And so 1.065, its average velocity was about 106 miles per hour. So the halfway point is going to be near the average. So I'm going to look at these speeds. And what I'm going to do is I'm going to add up, right? Because the area under the curve, if we look at our average speed that it's going, we're hoping that it will approximate both of those. Sorry, my phone is going off and I thought I had it on silent. So there, got it. So the average velocities within here, I'm going to start at the large size, and we know half the distance is about half a mile on this. So we'll add up the distances to the 0.6. So I'm going to do the same process. I'm going to look at my displacement, and I'm going to use my average. So I'm going to go to the sixth from 1 to 6. I'm going to multiply it by the 0.001, and now I'm going to add 41 all the way up to 119. I'm going to use that as, I'm going one little bit further than where I think things are, just because of early in the curve, it's going slower. And so that gives me 517, and if I multiply 517, I get about half a mile. So right around the 0.006 of an hour, it is going halfway. So what I did here is I added up to the 119, and the distance it traveled there was 0.517. That is really close to the halfway point for that. So I'm going to use this time as the halfway point. Now again, what I did is I used the average to point me in the direction of where the halfway point would be. The average velocity was just below 109. But because it has small values here, we're going to be somewhere near here. And if I kind of draw this out, let's see, 1, 2, 3, 4, 5, 6. Kind of looking at the total area that this curve does. And because this is such a steep rectangle over here in this last part, and this is really narrow, the halfway point's probably somewhere in here. Whoops, there we go. And so to estimate that, I added my way up to what was happening at the 6,000ths of an hour. And so I'm going to say at about 6,000ths of an hour, the car is halfway there. So 0.006 times 60 minutes times 60 seconds is about 21.6 seconds. And then in the last question it asks for here, let me get back here, is about how fast was it going. And because I was lining this up to measured values, I'm just going to read the velocity of 119 coming off of it. So that's kind of my approach to this. I used the average velocity to get a feel for where the halfway point was.